Example 1.2.7, an electric company uses pump storage of water as part of a hydroelectric plant. The plant uses a pump to draw water at a rate of 2.4 cubic meters per minute from a reservoir, and it stores that water in a 5-meter tall water tower. So a little typo there, sorry. Should be lowercase m, 5 meters. Find the work done by the pump moving water over 5 minutes, and assume the density of water to be 1,000 kilogram per cubic meter. So we're going to start like we always start. We're going to write our givens down. So go through the problem and extract that useful information. So we know that the flow rate of water is 2.4 cubic meters per minute. We know that the height is 5 meters. We know that it is a time of 5 minutes. And we know the density of water to be 1,000 kilograms per cubic meter. So this is room temperature density of water. Symbol for density is rho. So there we have the givens for our problem statement. Whoops. What are we being asked to find? We want to know work done in 5 minutes. So remember, work is a quantity of energy that we're trying to solve for. So this thing's pumping, it's doing work, and we want to calculate that over. So the
Strategy we're going to use is work equals force times distance. Formula that was given in the text, the distance of 5 meters.
So force, from physics, you probably remember force is equal to mass times acceleration. And so in this case, we're working against the force of gravity to pump the water straight up. So how much mass do we have? Well, it's density times the volume. Gives us the mass of water, so how dense is something, and then what is, how many cubic meters of it, for example, do we have, and what is the total mass of water we move? Well, that's where if we multiply the flow rate times time, that's going to give us total mass. So we kind of got to work backwards to get our mass. We get that from our volume and our flow rate. So some kind of embedded requireds that aren't specifically stated in the problem statement. So let's start by calculating the mass required. We can do that in one step by multiplying density times flow rate times time. That's 1,000 kilograms per cubic meter density of water. We were told that the pump was delivering water at a rate of 2.4 cubic meters per minute, and this was over a time period of 5 minutes. So what I want you to look at is we can see that if we cancel out all the units correctly, we should get the SI units of mass there, which you should know is kilograms. And so we do all that math, we see that the meters cubed cancel out, the minutes cancel out, and we're left with 12,000 kilograms, which we can also write as 12 e to the third kilograms. So that gives us our mass. Next, we need to know what the force applied to move that mass of water is. And so we've got the mass and then the acceleration, and we are pumping against the downward force of gravity here. So this is 9.8 meters per second squared, which is the acceleration constant g. Multiply those out and you'll get kilogram meters per second squared, which is a newton. And so the final answer is 117,600 newtons is the amount of force that needs to be applied for this to happen. So how far are we moving it? Well, we pumped it up 5 feet into the air, admittedly 5 meters into the air, so admittedly a small water tower. But if you multiply meters times newtons, you get joules, and 117,600 times 5 is 588,000 joules. So we look at that, and we know that at the end of the day, we know that the units of work has to be in energy. The SI unit of joules is J, so seems reasonable.